This is netstack.fm, your weekly podcast about networking, Rust, and everything in between. You are listening to episode 14, recorded on the 12th of November 2025, where Glenn has a conversation about PGP and DNSSEC with Arya and Terts from NLnet Labs.
Welcome in another week of netstack.fm. Today with me is Terts and Arya, and I am very excited about this episode. It's also the very first one where we have two guests, and they both work for NLnet Labs, a very exciting company which I'm afraid not many of our listeners know about yet. So I am also very happy that today our guests are able to shed some light on the fantastic work that they are doing. Some of the projects that we will be discussing is Roto as well as Cascade. But first, welcome Terts and Arya.
Hi.
So, as tradition goes with this podcast, I would like to know a bit about both of you first. So, Arya, maybe you can introduce a bit where you come from and how you got into this journey.
Yeah, hi. I've been programming all of my life, I think, which most of us can say. And I started out with, Java and C++, that sort of stuff. And I very quickly dived into the lower level things. I really enjoyed C, and that sort of dove into learning assembly and stuff. And I've always really enjoyed understanding how things work at sort of that level. I think about 4 years ago, I picked up Rust, and I don't know, I haven't really looked back since. It's sort of changed the way I think that I write code now, and it's really hard to go and pick up something else again. But I sort of ended up here through a slightly weird route. I think I met Terts and a few other friends at university, where I just looked for people who also really enjoyed Rust, and suddenly I was part of this group. And it turns out that they had begun volunteering for and organizing Rust conferences. So they've been doing Rust NL, now Rust Week, for I guess 3-4 years now. And so I naturally became a volunteer as well. And then I met Alex, who is now my boss, who was emceeing at the conference, I think 2 years ago now.
Yeah.
Yeah. And so, and I just sort of ended up here. It was just, I've really enjoyed the experience. But yeah, I think we'll talk more about NLnet Labs in a sec.
Yeah, very cool. And what about you, Terts? How did you get there?
I started here in Amsterdam doing a weird liberal arts and sciences degree that wasn't doing much programming. But I found this side job where I could do some programming on the side, and that was just a lot of Python and stuff. And at some point I found Rust, and I tried to introduce it there, but didn't really have much much luck. But then I did my master's in Delft, and there at that university, indeed, I found Arya and a bunch of other people who, I think the friendship really grew around Rust, and now it's much more, right? But that's how it started. Then we found that there were these Rust conferences happening. That was first Rust NL, kind of started as a local meetup, and I just started going there. Jana, one of our friends, was already involved, and then I sort of naturally rolled into organizing that too. So we did a couple of those conferences now. So we have Rust NL, and that now moved into Rust Week because we outgrew our local our local scale, so to speak.
It's been fantastic seeing it scale up from a tiny conference in Amsterdam, and now it's huge. It's been really fun.
Yeah, it's big. And then we found Alex emceeing that conference when it was being held in Amsterdam. and that just stuck in my mind. And in the meantime, I worked on the utils core utils project, which has now recently been added to Ubuntu. I'm not really involved anymore, but I worked on that for a long time, and even did some funded work for that. And when that kind of dried up, is when I was like, oh, remember that guy from that one conference? That sounded like a fun company. So I sent them an email, and they wanted to have me, which is how I ended up here. And that is now almost 2 years ago.
Yeah.
Very cool. And so now that we know a bit more about both of you, which is like a very fun and exciting story, I would like to know a bit more about the company as well, because we kind of got like already some glimpse of it. So I don't know who of the both of you, or maybe both of you, want to give maybe like an overview of the company and specifically also the mission.
I'm gonna let Terts handle some of this.
Yeah.
Okay.
So NLnet Labs is a company that's actually, well, it's an organization, a nonprofit organization. It's been around for quite a long time. It started in 1999. We celebrated 25 years recently, and it's sort of a spin-off of this other organization called NLnet, which is now very much focused on funding other open source projects that somehow relate to the internet. And NLnet Labs was a spin-off from that to do actually more implementation work. So that started with implementing DNSSEC, and then it kind of changed into that we maintain NSD and Unbound, which are these pieces of DNS software. Like NSD is an authoritative resolver and authoritative server, and Unbound is a recursive resolver. And those are like, they really blew up. They're everywhere. And those are, of course, they were started in like 2001 and 2007. So of course they're in C. But some of our colleagues had discovered Rust in the meantime before we joined the company, and decided that, well, at some point we should start doing our new projects in Rust only. So that's kind of what we're doing now. We have these pieces of software that are incredibly popular and that we really, really want to maintain. So we have a couple of people working on that, and then we have other people who make new projects in Rust.
Yeah.
And it's small. It's only 17 people. And we rely on funding from several organizations who give us grants, and also we offer support contracts where companies can just have sort of a direct access to our development team, and get help that way. However, we do have the rule that everything we do is open source. Everything goes onto the main branch. We don't have specialized versions of our software for specific companies, because we're really in it to, we'll just make really good software and help the internet forward.
Yeah. And we also participate in the in shaping the internet standards. So we have a lot of we attend a lot of conferences. That's also been really fun. But we interact a lot with things like the IETF, trying to shape how, especially proposals around DNS and BGP, so routing software, which is the other thing that we specialize in. And so, yeah, we deal with the implementation side, we deal with the standards, trying to bring everything together.
Yeah, very cool. And talking about the IETF, like in episode 11, we talked with Max Inden from Mozilla, and he had also a lot of great things to say about these IETF meetings, which are like a lot like conference, but are more like around together writing or working in these working groups. So I suppose you're all attending these as well?
I mean, so our boss Benno is the chair of one of the working groups. I think it's the DNSOP, or co-chair, I think, of the DNS
Yeah, that's
working
probably
group.
how it works. Yeah.
But yeah, so there's a lot of presence of NLnet Labs people in a lot of these things.
Yeah. We
Yeah,
personally we haven't been, but
Yeah.
but many of our colleagues are very involved in these working groups.
yeah. Well, Max had a lot of great things to say, and he said it was like very open, and like even if you're like, I mean, even if you're not a chair, but or you're not never been involved before, like it seems to be a very open group. So
Yeah.
definitely seems to be something that is recommended by him. Now we first introduced BGP in episode 11 when we talked with Ryan from Oxide. That was the first time our listeners learned about, and they learned a bit how it worked. Later in this episode, I want to definitely dig a bit deeper because a lot of your work is around BGP and it's a very important protocol still. But before that, is there ever like, I mean, as far as I can see, these original C projects still have a lot of traction and they are actually like different from your current Rust projects as far as I can see. At least they seem to have a different scope. I suppose that's on purpose, but even so, is there like ever a maybe like an idea of like, okay, once we maybe like have these other new projects at a certain, I don't know, stable point, we also want to port these? Or is there never like a question around like maybe they will just keep living forever?
I think there are. We do sometimes think about that, but we also just have people here who are just really like who know that software really, really well. It's really, really stable, and really, really important to people's operations.
Yeah.
So what we try to do is we try to provide like sort of more tools in addition to those, and maybe maybe a new tool we introduce can do like part of the work of what an NSD or an Unbound would be doing. But in terms of like really replacing them, there's no at
That's
least
not on the cards.
it's not
But
on the cards right now.
especially with yeah, I mean between NSD and Unbound. Especially with Unbound, it's something that's being used by a lot of people, and we're like we have to maintain that software. Like our mission is to continue providing for the internet, and through internet infrastructure, and Unbound and NSD are really, really crucial to that. So they're not sort of going anywhere.
We're also not like the organization also doesn't really believe in the fully rewriting everything strategy.
We're not the rewrite everything in Rust community.
Yeah. So but like that software has many years of tests and bug fixes and running and being used in operation. If you're gonna try to replace that with a new implementation, like you might do it in Rust, which helps alleviate some bugs, but you're gonna add a whole bunch of new ones in the process, which you'll have to fix, and would be a very long and tedious effort probably.
Yeah, I understand. And by the way, I love C. I mean, like I also know why Rust is there. I mean, but in general, for me, these are tools. So I understand your reasoning. And then in episode 6, we talked with Daniel from Curl, and that's a very stable software in C. And I think one way he achieves that is because he is still using like original, like even pre-ANSI C. So he doesn't like keep with the new standards. So he like, because a lot of times in these like memory unsafe quote unquote languages, it's often introducing bugs because they keep touching it, they keep changing it, they keep updating it. So is your strategy there also like we just keep with the original like version at that C was at that time, and we don't keep evolving, but we only like fix like issues when they are there, but we don't keep like touching it and introducing new bugs? Or how is your vision there on these projects?
It's not for us to say. We're not the ones maintaining that C code.
Yeah.
But from what I understand, they're not ancient C versions.
No, I think they do. The people at the organization who work on that, they do try to introduce new things all the time. It's not make it. Yeah, they introduced lots of, like actually right now there's like a big refactor happening that's being reviewed by one of our colleagues that overhauls some internals and tries to really make them better. So it's That's
Yeah,
not really
yeah.
the philosophy, I'd say.
Yeah, well, refactors at C, that does scare me. In Rust, they don't scare me, but in C, like, but I guess you have good reasons for it, and I'm sure you have very good people. And then the other reason why sometimes people rewrite in Rust is not so much because they want to rewrite everything in Rust because that's so fun, but more because, I mean, similar to some other, like, quote unquote, ancient languages, like, at some point it might be very difficult to find very skilled C developers. While it might be, well, not that it's super easy to find Rust developers, but still, it might become a bit easier in the future than C. So that's another reason. But I guess that's not really a concern for now. And maybe, I mean, are these projects ever also like finished? But I suppose not, because these specs also keep evolving.
Yeah, that's the main thing. There's always things that are changing. There's always especially with NST and Unbound, there can be security concerns, and there's always like that landscape is always evolving. So I don't think these pieces of software will ever be finished in any sense.
No. Some
No.
smaller pieces might be like it might be on like maintenance mode.
Yeah.
But NSD and Unbound, they're big and
being actively
yeah,
developed.
yeah.
Although coming back to your point about the different reasons for rewriting things in Rust. So one of the things we'll talk about is Cascade, which is our new DNSSEC signer. And the history there is that we did have a DNSSEC signer in C before this, OpenDNSSEC, which was introduced in about 2015. And so in that case, we are now, in some sense, rewriting it in Rust. But the underlying reason for this is more so that DNSSEC has changed. All of these specs have evolved a lot. Best practices have changed a lot. And so OpenDNSSEC architecturally is no longer at a good place where we're like, we can adapt this to do whatever we want. And so it just seemed like the right time to start from scratch.
Yeah, I mean, makes sense. And I suppose also a lot of lessons have been learned. And like usually with these projects, like once you implement it fully and worked long enough, you gain so much domain knowledge that if you would do it from scratch, you would anyway do it better. And yeah, you could kind of repeat it forever if there was infinite money and time.
Yeah.
But sadly not. So yeah, actually that's a good segue, or not segue, like that's a good continuation of our conversation. Let's continue over on Cascades. And before that, it's all about DNSSEC. But we never actually mentioned DNSSEC in this podcast, so maybe one of you could introduce our listeners to like what is DNSSEC and help them understand where it fits in the picture.
So DNS is, in some sense, a very naive protocol. It was introduced, decades ago, and it was never designed for an internet where you don't have trust. And so things like communicating in plain text and any sort of lack of authentication or verification means that we've had to adapt it over the years to try to account for the way the internet works now. And DNSSEC is a really crucial part of that. So DNSSEC is essentially, actually, I'll start over. So with DNS, you break down information into records. So you might say the address of google.com is this IP address, and that forms a single A record or a quad A record. And so you can consider sort of all of your information in DNS as broken down into these very small individual records. And when you want to query the DNS, you're asking for one or two particular records. DNSSEC tries to, the goal of DNSSEC is to assure clients that they're getting authentic information, that there isn't an attacker on the way who's changing the IP address that they should be talking to, or telling them this thing doesn't exist, or any number of other ways of manipulating this information. And the way this works is cryptographic signatures. So for every single DNS record you have, you associate it with an RR-sig, this signature record, which will contain just a cryptographic signature over that material. And there's all sorts of additional considerations. It gets incredibly complicated. There's, as a simple example, you need to also keep track of non-existence. So, for example, if I just gave you a signature over a record, right? An attacker could still say, well, this thing doesn't exist. And there's no way. You also have to authenticate the non-existence of things. If you as a user are trying to access, for example, Google.com, and an attacker says, well, that doesn't exist, right? They can block off that access in a way that you can't tell that something went wrong. From your computer thinks that, oh, Google.com, it just isn't a thing. But DNSSEC also accounts for authenticating non-existence by introducing these additional NSEC records, and then signing things over there. Essentially, my point is there's a lot of weird edge cases, both due to just the history and the evolution of DNS, and just because security is really complicated. And so that's sort of what DNSSEC as a whole is trying to do.
Okay.
Yeah.
I understand. So it seems all about like proving like that something is like valid, is authorized, exists, etc., which traditionally didn't exist. Like originally like DNS, and now we come perhaps more in a different realm, like in privacy rather than like security. But like traditionally DNS was served over just UDP, and now they're also moving it to HTTPS. This kind of DNSSEC thing, is it ever also done in plain text? Because I guess it could, because in the end you're not really leaking anything private, or does it not matter?
So the original DNSSEC RFCs talk about, what their security goals are, because the DNSSEC is here to sort of assure the authenticity of your data, right? But it cannot assure privacy, and it cannot assure availability. An attacker can simply not talk to you, right? They can block off your communication. There's no way to work around that. DNSSEC inherently does not specify any means of encryption or sort of hiding your requests. It's just adding more information to authenticate that the responses are valid. So traditionally, DNSSEC is also done in plain text. And yes, there are now a lot of attempts with DOH or DOQ to try to address the privacy implications, but fundamentally it's a really hard problem.
And why is it specifically a very hard problem?
Well, if a user wants to request certain information, right, they now need to ask somebody, some DNS server, for that information. That DNS server inherently needs to know what the user's asking. And with IP, you can always, there's a million different ways to trace people, between fingerprinting of DNS software, just tracking IP addresses, looking at things like timing patterns, things like that. It tends to be really straightforward if a user's talking to a single server, to figure out who they are, and where they're asking from, things like that. And that's, you can try all sorts of interesting schemes, like saying, I'm going to ask from different places, or I'm going to ask different servers, but I think fundamentally there just isn't a good answer.
And the solutions that are being proposed are kind of like the kind of proxy things, I think.
Yeah.
So you send a request to some other DNS server that can then send the request for you, but that now means that you have to. It's kind of like a VPN. Like you have to trust the VPN provider now, or like that other resolver. So ultimately, you have to trust somebody who's going to read like your actual request and do another request for you. You have to put your trust somewhere. You can scatter and you can try to hide and do dodgy things, but it's a hard problem.
I think another way of looking at it is as a trade-off between privacy and efficiency. So if you were to use something like Tor, right, that could get you that degree of privacy, but it comes at an efficiency cost. And when DNS is being used by literally every single internet application, right, that's not a cost you can pay.
And there's one more thing that I think we should address here, which is that what these schemes of like DNS over HTTPS do provide is that whenever your request is in transit, then at that point it's not in plain text. So you always have to trust somebody, but at least with these schemes, it's not unencrypted on the wire. which
Yeah.
does
I mean, that's fair.
Yeah. There are also, I just wanted to quickly mention, there are also additional, this is something that everybody's thinking about. We have ideas like opportunistic encryption. There's the whole DELEG working group that are trying to address that, which I don't want to get into. And yeah, basically this is something that's on everybody's minds, but it's sort of just a hard problem even on paper.
Yeah. No, that's fair. And I thank you very much, even though I put you a bit on the spot. I really like your answer there. Now, as a, let's say, website administrator, it's still up to me to enable like a checkbox in my DNS registry to enable DNSSEC. Like, is there a reason why this is not just the default and you have to kind of opt out of it? And why would you ever not want it?
Yeah, that's a good question. I like we're not domain registrars. We can't really speak to what that experience is like, but I should say that there is a history of DNSSEC is something that, from our perspectives as implementers, feels like something very obvious. Um, but there has been a history where people feel where DNSSEC has hurt people or where it's caused zones to not work properly and things like that. And while the entire community's tried to address that history and resolve those issues, um, some of that, like those emotions, don't leave. And working around that is really hard. So there's still a lot of people who might feel wary of DNSSEC, right? And that's understandable just based on the history. And so yeah, I understand that it doesn't feel like 100% thing.
it also makes things slightly more complex,
Sorry.
right? Like
Yeah.
it adds some operational overhead.
Yeah.
You have to now think about, I don't know, keys and things, and
Yeah, there's a lot of operational effort that goes into that, and it's not a like OpenDNSSEC when we collaborated to build that in 2015, it was sort of designed as this one button. You just use this and suddenly you have DNSSEC and you don't need to think about it, right? And while we still think that's possible and we're still chasing that, there is a lot of inherent complexity that you have to take on when you say, I'm going to use DNSSEC now. And that doesn't really go away.
Yeah. Okay, cool. And so I feel DNS is one of those protocols that carry a lot of weight. It's kind of like saying I implement HTTP. Like you're talking basically about like a million RFCs. And I feel with DNS, it's pretty much the same. And then so you have like in Rust, I think the biggest open source project around DNS is Hickory DNS, and they provide a lot around DNS. Is that something you then also work together with? Because I imagine, okay, you have the DNSSEC signer. Like it's still hard for me to figure out where in such a stack the DNSSEC signer fits in. Like, is it something that you plug in there? Is it something that you work with church providers? Is it something that you just run separately somehow? And then if so, how is the flow like? Yeah, I try to understand a bit like where it fits in there.
So Cascade and OpenDNSSEC are called bump in the wire DNSSEC signers. What that means is you have some DNS operator, right? For example, .com or .fr, right? And they have a DNS zone, which is essentially just a massive list of here's every single domain name under .fr. And in order to resolve the actual records within that domain name, you should go talk to somebody else. So these are essentially a long set of delegations. And that comes down to the way that DNS is structured as this sort of distributed protocol. And yeah, so within the DNS operators sort of internal pipeline, right? They will collect DNS. They'll collect all this DNS information, for example, through different registrars. And then they have a DNS zone, which is a collection of all the records under, let's say, .fr. That can be served by a DNS server internally, right? Just like they might have an internal hidden DNS server, which is like, here's all of our DNS records, right? And normally you would then forward that into a bunch of public instances. So for example, you might have 20 different servers spanning the globe, which are the authoritative servers answering queries for what is foo.fr. Now, OpenDNSSEC and Cascade, as these bump-in-the-wire DNSSEC signers, sit in between those two things. So you'll have your internal primary source of DNS data, and that does not include any signatures. Then OpenDNSSEC/Cascade would consume that data and expose a new DNS server serving the same DNS zone, but now signed with all the additional records you need. And then that would now get picked up by all of your public servers. And now suddenly you're serving DNSSEC signed data.
Okay, but
So it's
am I then correctly to assume that it's kind of like a man-in-the-middle proxy, or am I seeing it wrong?
Kind of, yeah. So it's a daemon that they would be running internally, and they just need to point all of these public instances, however they distribute that DNS data, at this thing instead of their internal DNS source.
So that also means in case they support DOHH, then they would be the one that terminating also the TLS and doing that part, and maybe internally they do it much simpler or something.
So they would so wherever I'm just going to say Cascade now, but so wherever Cascade sits, their downstream those public servers, right? Cascade is supposed to be hidden. It's not going to be exposed to the public, but those public servers would then fetch the entire zone contents, and there are efficient ways to do this. There's diff-based mechanisms. And so each one of those servers would probably hold an entire copy of the zone data, and they would be serving that themselves using whatever transport mechanisms they need to.
Yeah. So individual queries never go to back to the signer.
So the signer is just sitting in one place, and it doesn't actually experience that much load.
It exports the entire zone to the other servers, which then resolve the individual queries and do all sorts of things.
Okay. And then what I also trying to understand is I suppose it makes it easy to adopt or to provide adoption by providing a separate daemon, because you can kind of almost plug it in, kind of like a reverse proxy. But let's say once it's more established, is there also not good reasons to just have it included in your regular DNS server?
So, one of the things, and this also comes back to the sort of history and trust for DNSSEC, which is that we want to build something like DNSSEC is really complicated, and we wanted to provide a product where DNSSEC is its one and only purpose, right? And so there's less of a concern that there's going to be different interacting parts and DNSSEC gets lost somewhere along the way. The entire focus of this thing is to just do DNSSEC. The other reason to have it as a separate daemon is that it will often need to do work itself, in the sense of, for example, DNS signatures can expire. So occasionally, even if the contents of your zone haven't changed, sometimes Cascade will be like, oh, hey, I have a slightly different zone now, because it had to refresh some signatures. Concerns like that, especially, we're not touching on the elephant in the room, which is DNSSEC keys. Key rollovers are perhaps the most complicated aspect of DNSSEC. And so having a dedicated piece of software that's just I'm just going to do DNSSEC now, and the operator doesn't have to worry about what else it's trying to do, for example, we find that that's been really valuable.
Yeah. And that also provides kind of more transparency about what it's doing. You can view its logs to just see the DNSSEC things. And another thing that we provide is these review hooks, where Cascade will expose the zone before it will do its signing and after, and then you can inspect those before you actually publish it. So because it's this extra step in your pipeline, you can inspect the before and after, and then hit a button to say, now I actually want to, this looks good. I verified this with various pieces of software. Now it can go to the public. In that way, it's really meant for, big important zones that really need to ensure that their data is correct.
Okay, that's very cool. That makes totally sense. And then, we originally wanted to do the recording with you folks a bit earlier, but you were working very hard on like,
Yeah.
I believe it was the Cascade
Yeah.
0.10 alpha release.
Yeah.
So congratulations for that. Seems to
Thank
have
you very much.
turned out very well. And that celebrates also 15 years of open DNSSEC. Now, you do state like, okay, do not use it in production, but at the same time you offer like paid support contracts. So does that mean that like, I imagine if someone works with you commercially, then maybe it does make sense to already use it because you can offer like support and you can integrate it correctly, or is it like for now actually not at all used in production yet?
So it should not be used in production right now. It's still alpha software. We're still working out. Our sort of goal with the alpha was to at least have to be able to show people what sort of user experience we're aiming for. And so the internals have like we're still streamlining everything internally. And so yeah, we are talking to some operators, but they're only trying it out in testing environments. There's no production usage of it yet.
Yeah, so the support contract is for us to have the money to develop this further, and then we can help them, with any issues that they find in their testing environments, and ensure that this will become production ready.
Yeah, and so intuitively, I would think, given how like valuable the software that you make is and how important these protocols are, it should be possible to get from important enough players support contracts. But at the same time, I know companies also do not like to pay these. Like, I mean, I don't know, like at least personally, I find them that they much easier pay like a big enterprise for some bloat software than they would pay for something like this, which might give them a lot more value. But I'm not sure how your experience is, or maybe that's far away from your like area of work.
It is not our area of work. We do talk to Alex a lot, who is the main guy doing that kind of work. I'd say it's very it varies a lot between different companies. Some companies say like, oh, we want to have support contracts for all our critical pieces of software because that's our policy, and we want to make sure that we can talk to developers and get bugs fixed whenever we need. Other companies are way more relaxed about it, say, where they say, well, as long as we're not experiencing any problems with it, we could just take it, and that's fair, right? Like we distribute this as open source software, and you're free to use it however you want.
We do rely on grants and funds.
We do, yes. But yeah, it's this like weird double thing where it's like, you can use it, and we also want it to be available to companies with a little bit of less cash. They don't, we're happy to help out and happy to give them software. But yeah,
Especially, I think I should also give a shout out to the Sovereign Tech Agency, which has funded a lot of our work. In particular, they helped us build up our DNS library domain, and now we have just started working on another grant from them for certain features within Cascade for the production release. So there are these organizations which are which we're incredibly thankful for, which are able to give us money. Like NLnet Labs is reliant on this sort of revenue.
Cool, fair enough. And then so I want to switch a bit also to Rotinator and like BGP, and I think later we will go a bit also back onto Cascade, but more in the light of another topic. But I first want to talk a bit about Rotinator before I forget, because actually that's originally how I discovered you guys around the language like Roto, which sadly I don't find much information about on your website. Like I find a lot about Rotinator, but Roto is like a bit in the shadows, despite I find it a very exciting project, but I suppose it's more a means to an end, so I do understand. In episode 12, we talked with Ryan Goodfellow from Oxide, and he gave a nice introduction to BGP, so I don't think we have to do that again. But we will talk, of course, also about the BGP protocol. Now, before we begin, like, what was the reason that you actually like created Roto and that you felt like a need for having to invent a language there? Because it's not like there is not a sufficient amount of scripting languages already. Both in general in the software world, but also specifically to Rust. So I imagine you had some good reasons there.
Maybe
Sure.
start with
Rotonator. So first, to clear up a little thing, is that we have some similarly named projects. There is Rotonator, Rotonda, and Roto.
Sorry.
Rotonator has to do with RPKI. Basically, that's also providing like sort of authentication and stuff to the BGP protocol. And then there's Rotonda, which is our BGP collector. It's kind of this thing that you can use to monitor what happens with your various BGP routers over time, and it kind of can collect that data and then allow you to access it, query it, look at it. And then Roto is the scripting language that we have for Rotonda.
Yes, thank you for the correction. In my notes, I wrote Rotonda correctly, but somehow I stopped reading my notes.
It is kind of confusing. I do agree. So the need for Roto came from came from Rotonda, right? So Rotonda, like I said, is kind of this thing that ingests a lot of information. You can kind of just see it as a big database that just this BGP and BMP, which is like a monitoring thing over BGP, gets put into. And a lot of data gets transmitted over BGP. There's like these big waves that happen in your network. Whenever something changes, all of these routers start talking to each other and correcting the information across the whole network. And that just kind of is a continuous process. So a lot of data comes in. So first of all, we need a database that can handle that. We need a database that can store that information efficiently, query it efficiently, and that's all the responsibility of our colleague Jasper. He's made a great database specifically for that purpose.
Yeah. Wow.
Now the second problem we have is that there's a lot of data coming in, right? There's just a huge stream of data, and you usually want to filter that somehow. So most routing daemons have some way to specify filters over data. And you can use that, for example, in a BGP router to make decisions about what paths you actually want to distribute or to accept, or there's various kinds of things that these operators want to filter on. Maybe they want to change some data. Maybe they want to fiddle with it. Like, you have to understand that this is all these operators. They're dealing with like physical connections to their peers and like several agreements that they made with other people. So they need a lot of control there. So all these various routing daemons that exist have ways to filter this data. And what we wanted to provide is also that, but we didn't really think that all of these solutions that were out there were good enough for our purpose, because we need this high speed, and we also, just as important, is reliability, right? We kind of want, when you write a filter, that should just work. It shouldn't just crash because, I don't know, you're trying to assign a number to a string, right? We want to ensure upfront that there's some correctness to this thing, at least from a type perspective. So those two properties combined, we want the speed and we want the reliability, that made us decide that we wanted to go for something that is statically typed and also compiled. And even before I joined the company, this was like an idea that had floated around. There was some prototype of Roto that was very different from what it is now. It also wasn't compiled yet, but it was like this filter thingy. And then when I joined the company, I think the people here looked at what I had been doing at uni, which was a lot of programming language stuff, and they were like, "Okay, well, you go do that." And I was like, "That sounds great." So. What we did is we looked at this thing called CraneLift, which is a compiler backend written in Rust. It's kind of like an LVM alternative with a focus on faster compilation but less optimization of the final code. And the idea is we make a language that targets that, and then CraneLift has this beautiful thing to create to just compile that in memory. So it will create this. It will compile it to machine code, and that machine code is just available to you, and you can call it basically. So that's what we're using there. And then and over time, this grew into more and more of a sort of serious scripting language, because we figured that if we want to provide to people something that is kind of familiar, we actually have to provide something that is, close to what they would expect, like with a sort of more familiar syntax. And so instead of going for sort of specialized syntax towards BGP, we're trying more toward going towards sort of general scripting language that we just provide a lot of, functions and things like you would do in any scripted language to handle this BGP data.
Talk about the magic.
What magic?
The FFI, the integration.
You're right.
It's like the most important thing of Roto.
So the final part here is that there are some scripting languages out there, but they usually have some like C FFI. So you talk to them via C, or they have to do some deserialization step, or serialization and deserialization into the values of the language, right? So for example, most Python values are like dictionaries of various fields and values. So whenever you want to take a Rust value and you want to make that accessible to Python, you turn it into that dictionary, and then when you get the result back, you convert it back. Because we want that speed, not only within the execution of Roto, but also passing things to and from Roto, we have focused on making the integration with Rust really tight. So because Roto is entirely written in Rust, we can really efficiently map these Rust types to Roto and back. And you can register your types, your Rust types in Roto, which means that type will now become available in Roto if you're writing your scripts. And then you can also provide functions and methods and constants and all those things to be able to work with those types from Roto. So from Rust, you can call Roto, and then Roto can call Rust functions again.
And that means you can also like pass data, including even like streaming bytes or something, or that's outside the scope?
Sure, yeah. So the one limitation is that whatever data you have, it needs to be cloned, right? So Roto will do a lot of additional clones of the data just to be able to provide more of that scripting feel, because we don't want references and those kinds of things.
But usually you just wrap your data in an arc and call it a day, and it'll fit through Roto.
Yeah.
I think the only actual limitation is that generic types defined in Rust cannot be exported as generics into Roto.
Yeah.
But other than that, it's kind of magic. You can sort of like you've had some demos which you presented where you could interact with Bevy, which is this Rust game engine, and control that from Roto, because you can just directly expose functions which will talk to Bevy to the Roto code, and it's incredibly efficient.
Yeah.
Oh, very cool. Yeah, because like that's how I discovered you, because we maintain a framework called Rama, all about networking. And we were thinking of it as the scripting language beside WASM to really control like middleware and even leaf services. Now, those are for protocols like HTTP and similar things, including mail traffic and whatever. But I suppose it should work. The only thing, it seems, I need to be like clonable. Or do you see some issues there or things where we might be stretching the scope of what Roto might be about?
No, I think that's a good a good use case for it. Like it really shines in these cases where you want to provide some scriptability, but that script will be called many, many times, right? Which indeed for like the same proxy kind of idea, like application, is really the case. Like you write once, and then for every request or something, you want to execute this code, and that's kind of where it shines because we do this compilation step and this type checking step, and then we can provide this efficient execution. Funnily enough, there is somebody outside of NLnet Labs who's picked up Roto in their own project. They go by Algernon online, and they have this thing which is also kind of a proxy that you put in front of your web server, and then it will try to detect AI crawlers. And if an AI crawler is detected, then it will just generate it. It will generate garbage for it, because that is actually cheaper than serving the actual content. So it's kind of to protect these all these web servers that are now being that now have high costs because of these AI crawlers. So that's actually kind of a similar case where they've integrated Roto, and they so the rules for detecting these AI crawlers, that's what they have programmed in Roto, and they have both a Roto version and a Lua version, and it does look like Roto is consistently a little bit faster there.
Oh, very cool. Yeah, definitely link it to me. I will also put it in the show notes. That's a very interesting use case. And so another thing I like usually about this language, and I hope it also works for Roto, is the fact that you might have like a proxy running on an end user device or a router or somewhere in the cloud, and you need to hot patch it. So you say like, I want like a new version of these scripts, but you say, okay, we have to compile in crayon list. I mean, does it mean I can just, I don't know, embed this compiler inside my process or something, and like I receive a new version, I compile it. If it compiles, I can assume because it's compiling and also the fact that it comes from a source I trust, that it's fine to replace it. I mean, is that more or less what I can do with Roto? Or am I saying
exactly.
Yeah.
So the way that you use this thing is that the host application compiles the script while it's running. So you can do that, and how you do that is up to you. So you can either decide to just load the scripts at startup, and I did this in the demo that I did. This was for the Eurorust presentation that I did, which has now recently also been published. So you can look at that. What I did there is on every frame, I did a quick check on the script and what the modification time was of the file. And if that was newer than the last one I had seen, I would recompile it while the game was running, or sort of visualization. It wasn't really a game, but it was a visual thing. While that was running, I would recompile it and then just pass that new function to the component that would actually call it, and that would actually allow for sort of seamless updates to the script. So I could just save a new version of the script, and instantly it would update on the visualization.
It's very cool.
I mean, that's cool. Yeah, I'm gonna link to that talk as well. I mean, and originally I come from the game industry, and yeah, we would indeed use scripting languages like that in the past, because yeah, if you had to compile all the time C++ and your entire game engine, it would take forever. So yeah, that's very fascinating, and but even doing it every frame, I mean, that's crazy, but could result in some very interesting properties.
So I was just checking the modification time every frame. So only
Yeah.
when that was necessary, I could do a full.
Yeah, of course.
Which would, but still, you would barely notice the like. I had a little graph in the corner to show the frame count, and it would like dip slightly when a compilation was happening, but you wouldn't notice too much.
But I imagine you could even just do it like you could check it, but then even if it's different, even that you could do, I guess, in the background and do something like an arc swap, or I don't know how you like replace these things. So but that's very cool. I like it. And but what I didn't get an answer on is like, does it mean that you need the CraneLift compiler inside? I mean, is it like something you can use as like a library, or how that works? Like, because something has to compile it.
So the CraneLift is actually just a Rust crate. So it's just in your binary. If you include Roto, CraneLift comes with it. You don't need an additional library for it installed. It will just be compiled in.
Well, very cool. And does that mean that you can even like compile Rust on the fly and have that as a plugin, or is that something? Am I going too crazy here?
Yeah, not really. So CraneLift is only a compiler backend. And so Rust can be compiled with CraneLift, but you need the Rust compiler front end for it, and like the rest of the Rust compiler. CraneLift is only a part. It's like the last part, like that does some internal representation that they have, some special sort of simplified language, and they turn that into machine code. And the Rust compiler can also output that. But you need the whole rest of the compiler toolchain to do that.
Okay. And as a Roto user, do I have to even care about the fact that it's using CraneLift? Do I just import the Roto crate, or do I also import something like CraneLift myself?
It's just Roto, yep. And Roto will do all the compilation for you. And
well, that's very cool. Like, yeah, I mean, it sounds super exciting. You can definitely shout more from the roof from it, because among all the Rust scripting language, I think it's very exciting. And now how you're describing it, you only made me more excited. So yeah, I mean, I honestly don't think many people know about it. Like, I guess your Eurorust talk helped a bit there, but yeah, definitely keep shouting.
I think it is picking up some traction, but it's also new, right? It's new, and it's still lacking some features. For example, right now I'm really working on implementing lists, which like I guess people sometimes look at a language like this and say like, oh, but it's lacking this one thing, so I'll just shelve it. And so part of what I'm really doing right now is trying to see what features people really need from this to have it be useful for them. But it is a new project. And also what is interesting is that because it's this compiled thing, there are some things that I think the sort of more interpreted languages, dynamically typed languages get for free that we don't. So for example, with these interpreted languages, you can do lists quite easily because, well, everything is just a value in your language. It doesn't really matter what kind of value it is. If you have a list, you can add anything to that list. It's fine, right? You could want to add a string, fine. Add a bool, fine. It's still fine. It's now a list of strings and bools. But what I have to do is I have to look at I first have to implement like some kind of generics, right? It's a list over a certain data type, and then I have to compile that properly and make sure that I get all the things right there. I need to make sure that this list works for any data type that you pass into it. It allocates the right amounts of memory.
There's a lot of work.
That just makes it makes some features more difficult and slow to implement than other languages.
I've been helping you out with some of the implementing generics in a language is like just so complicated. And I've been helping Terts out, or like we've been talking through a lot of these features. It's just like, this is so much work, especially with like as you're saying, like lists in terms of a runtime are one thing, but when you need to now start type checking them, right, and doing code gen, it gets really complicated.
Yeah, for sure. I understand. Like, as you usually don't think about it, but when you implement these languages, like, it very much becomes complicated. So props for you on that. And I would hope that you also get some external contributors and maybe some people like funding, like if they actually commercially use it, because similar like Rotonda or Cascade, I mean, it seems like something worthwhile to fund if you rely on it. So why not?
That would be lovely. What we do also see is that we've been showing off Roto whenever we've been showing off Rotonda, and that is also kind of interesting to see, is that it provides us, by being the sort of general scripting language, it provides us so much flexibility that we can say like, oh, you can also do this quite easily because, well, you have a scripting language right here, so just do it. And so it's been kind of a nice selling point there. And so it does also feed into like the funding for Rotonda. It's very much part of that project.
Okay. And then like BGP collectors are quite interesting and also are, yeah, still like, I've not been in contact with them a lot, like as I'm using them myself. I know in general like how BGP works. I also know where it fits. But then I suppose it also means that you collect historic data and make it available or not?
Well, depends on what you mean by make it available.
Well,
But
not you, but I mean the one that you would use Rotonda. I mean they would have also historic data, I suppose.
they would, yes. So Rotonda collects this data, and it does that by first keeping it in memory, and then whenever something gets overridden, it writes it to disk. And that's how you can sort of have this big database of what happens over time, and you can query that, export it, however you want.
Okay, and I think that's the kind of stuff that's used by researchers and ISPs. Is there like also an actual real-time operational use case for that?
Yeah, I think so. So indeed, researchers and ISPs, but also, it's nice for people to see what's going on in their network, and how things have changed. So like it might show you. So let's say something goes wrong in your network. Yeah, you're an operator and something goes wrong in your network, then you might want to see, okay, where did this thing originate? How did the other routers react, or how did they try to mitigate that problem? How did that fail? What exactly happened between all these various stations that you have?
Okay.
And if you have them all hooked up to Rotonda, then and sending their data, then you can actually see that.
Yeah, I mean, and sometimes these things do happen. Like you sometimes hear about BGP fallout. I think the biggest one from recent history that I remember is the one from Facebook.
Yeah.
Is that something where a BGP collector was probably also used to help them diagnose it and figure out what went wrong, or how would that work?
Probably, yeah. Yeah. I think to diagnose sort of retroactively at least. I think there's also there's also things like what they call BGP looking glasses, which is sort of a collector without history, just to see what's currently going on in your network. Those are also very popular to just have a sense of what's going on. But then definitely they have some collector thingies going on to diagnose the issues when they go wrong.
Okay, and then I mean BGP is so I mean, despite most people don't know about it, we try to of course shed a bit of light in this podcast on these kind of protocols as they're very fundamental to our world. Like I imagine there must be already plenty of other BGP collectors. Like what was then, for example, the reason that you felt it was important to start Rotonda?
So there are some other pieces of software that do things like this, but I think what happens usually is like you have these sort of BGP daemons. There's various things like that just they do. So a BGP collector and those kinds of things, what they kind of do is they pretend to be a router usually, but they don't send anything. They don't send any updates, so they just ingest. They start BGP sessions with their peers and then just ingest that data. And that certainly happens. And then people put that in the people put that in other databases and stuff. So I think there's like Go BGP and some other pieces of software. I think also some Python stuff that people just kind of modify or use like plugins or things to then essentially pipe that information into databases, and sort of they can query that. Rotonda is meant to be sort of more of a one-stop shop, where we do all the BGP sessions for you. We keep track of the BGP state, like what the current routes for everything are, and that kind of stuff. And we keep track of history for you. And by doing all of those things together, we can be very efficient, and just sort of provide a more comprehensive package in that way. I think that's the main difference from the existing software.
Okay, yeah, that sounds like very good reasons to me and very exciting. Now, I also wanted to talk a bit more about it seems that all your projects operate at a enormous, gigantic scale, or at least are meant to be. Like you're like piping a lot of traffic through these kind of projects. You also don't want to spend too much resource on these. So that brings it automatically in the territory of like zero copy handling, SMD, all those kind of things.
Yeah.
Like, I mean, I imagine in both projects, so I leave it up to you. Like how I want to first start off in like, what kind of special considerations do you take into this, like making sure it's like performant enough that you are not allocating too much, besides the fact, okay, you're already using Rust, it's already like not garbage collected, but beyond that, like how do you go the extra mile there?
Do you want me to?
I'll leave it up to
Okay.
Arya. This is Arya's specialty.
Okay.
Optimization is my favorite thing. And yeah, like understanding how do you build something that can scale in this way is it's really difficult. And usually, like, you can look at, there's so many different levels that you can optimize at. You can optimize like your network bandwidth. You can optimize the even the asymptotic complexity of the algorithms you're using. You can optimize the system calls you're performing. You can optimize your data structures, how much memory you're using. You can optimize how many allocations you're performing. And at the lowest and the best level, you can literally optimize individual instructions, right? And it's all about, what does your application look like? Where are the hot spots in your application? What do you really have to think about? And so I'll quickly touch a little bit on the Rotonda case, which I haven't really worked on, but the person who mostly spends their time on that, which is Jasper, has talked to me a bit about the performance considerations for Rotonda, and especially their internal database, the Rotonda store. And the sort of biggest driver there is not the network bandwidth, it's not really system calls, it's about the data structures, right? And it's about, well, how do you store less data? So for one really small but interesting example that we saw was within the Rotonda store, you have to keep track of, I think it's for every single router peer you have, you might store some auxiliary data, which is essentially just a byte buffer. And previously inside the Rotonda store, it was being held as a VEC of U8, right? Now, I'm not going to so just thinking about, I have like 100,000 or a few million VEC of U8s, right? What does that translate into? A VEC of U8 in place is 24 bytes on a 64-bit computer. And that's just overhead. That's not the actual data that you're thinking about. And so now automatically that's, 24 megabytes or however much data that you, like, that is not inherently part of the data you needed. It's just a bunch of pointers and capacities and lengths and stuff. And so how do you optimize that? So one of the things we notice is, well, we can actually cut off, we can merge the capacity and the length. This is not something that needs to grow dynamically. So you essentially replace it with a boxed slice, right? So a box of slice of U8 is 16 bytes, while a vec of U8 is 24 bytes. And that's because a vec will hold some additional capacity, which you can now add into or remove from. And we didn't have that need. So suddenly we dropped from 24 bytes to 16 bytes. And then we noticed, well, actually, we have this hard limit that all of our data will fit within 64K, right? And so we can actually go further and say, I don't need a 64-bit pointer and a 64-bit length. I need a 64-bit pointer and a 16-bit length. And now we've dropped to, so now we have this specialized type which handles these byte buffers, and it's exactly 10 bytes in size.
And just to quickly iterate why this is, like, why these few bytes improvements are really important is what this store is doing. Is keeping a full table of like which IP address can, like, what path do I need to take there. And I think it also does that per peer it talks to. So if you talk to 3 routers, it stores 3 versions of each of the paths. Now you can imagine if you need to do that for every, even just IPv4 address, right? That is already a huge number of entries in your store. And then we also have IPv6, which is even way more possibilities.
So, like, in terms of what the Rotonda store needs to think about, right? Like, my understanding is that you might have gigabytes or tens of gigabytes of data in memory there, right? And so when we're making such a small change as saying, okay, I took my vec of U8 and now it's 10 bytes, right? That's like a 2-fold reduction of this one component. But that can mean a lot in terms of reducing the overall data structure sizes. And then you can go further and you can say, well, I'm going to actually coalesce all the data between all of these byte buffers. I can try to reduce the number of allocations I was performing. I can try to group these in different ways. Like those sorts of, I think those sorts of data structure optimizations are often the biggest and most important things that you can optimize in most applications. Especially like if you're ever in a case where you're like, I have a gigabyte of data, or I have 10 gigabytes or so, and sometimes you'll run into those cases with DNS software, especially, and then you're like, well, how do I really tackle this head on and try to find ways that I can make all sorts of incremental changes? Because even something as small as saying my 24 bytes has become 16 bytes, right, can save you gigabytes, just depending on what your application is doing.
Depending, of course, on which part of the software you're looking at. We only do this kind of optimization for, well, we're talking specifically about the Rotonda store because that has those kinds of characteristics where that is really important.
But then you also, I think there have been some attempts to look at zero copy for Rotonda store, but I'll mainly talk about that in the DNS context. So within DNS, you run into all these really interesting use cases. For example, so .com, right? The .com zone is the biggest zone. It's sort of the worst case scenario for any DNS software, right? To the extent that most open source public DNS software doesn't try to address the .com case. Like .com will contain, I think it's around 300 million records, something like that. Like 300 million, within there is all of the domain names, and there's also like the auxiliary data that you need to actually use those domain names.
How big was the zone file you got? How many gigs?
So for research, normally .com is not like a publicly available file containing every single record. But for research, there are different ways to access it. So for example, we have a text file here, which is just the .com text file. It's, I think, 24 gigabytes. And then you're like, well, if I want a DNS server to serve .com, right, I need like 128 gigs of RAM or something, like even like in some ways that textual zone file format is more efficient than what you'll be storing in memory to serve this, right? You need to be able to access that information efficiently, and then suddenly everything gets way bigger. And so one of the things that I've been slowly approaching is how do you optimize these data structures? How do you not only improve memory usage, but also improve performance? I think one of the things that most people don't realize, or that people misunderstand for whatever reason is that optimizing your data structures, reducing memory usage, will almost always also improve your performance. Like these days, if you have gigabytes of stuff, your biggest bottleneck is memory access, almost always. And so just storing less data means that things stay in cache better. Like your access will get more predictable. And in the end, you'll just also have better performance. In fact, it's really hard to optimize the data structure so much that now you're like, any further optimizations I make will either improve memory usage or performance. It's actually really hard to get to that level. And for so I'll quickly touch on just like some of the vague optimization techniques that you can sort of strategies that I really like applying in these cases. One of them is to just try to specialize and segment your data depending on what it is. With DNS records, especially for the big zones, you'll maybe have 4 or 5 different kinds of DNS records, right? It's not actually a wide variety. It's just like, I have these 4 or 5 things. I can actually now build specialized structures to manage each one of these. And then within that, I can now try to optimize like individual bytes away, right? Optimizing individual bytes for a certain kind of DNS record can be a massive improvement because you might have 100 million of those records, right? And so as a simple example, within DNS signature records, right, which do contribute to that 300 million, all of those, the sort of wire format representation of those DNS signature records include some redundant information. It will tell you, for example, which cryptographic key was used to sign this record, which is probably the same across all of your records, right? You usually only are signing with a single key. And so moving that data out means that you save, I think 5 or 6 bytes over a few million records. That's a massive improvement. Those sorts of, so essentially specializing, understanding what your data looks like, and then specializing to store that in, just in better ways. That's often like the biggest, most important thing you can do. But that's all from a DNS storage perspective. So I actually listened to the episode 10, I think it was with Joshua Liebofieser, about zero copy, and I found that really interesting. So everything I've talked about right now was from the perspective of a DNSSEC signer or a DNS server, right? Where you just have this massive DNS zone and you're just working with it. But that's not actually the case for most DNS software. Usually you're talking about, I'm a DNS client or I'm a DNS resolver. I'm just communicating over DNS, right? That's your main use case. So NLnet Labs has their own DNS library, right? It's called Domain. And it's sort of a general toolbox almost, where it will provide facilities for handling zone files, for representing all your different kinds of records, for performing DNS queries, and for serving DNS. It has different facilities for all of these things. And when I joined the company about a year ago, one of the things I was most interested in was in Domain, and how, are there ways that we can make this more efficient, right? Because the core facility that this thing needs to do is network communication and transferring data over the DNS wire format. So I made a big push for changing how the Domain API looks so that it can apply zero copy in a lot of cases. Along that journey, I also spent a lot of time looking at the zero copy crate. And I think in that episode, Joshua had mentioned that zero copy can't handle variable sized data or variable sized fields.
Yeah, correctly. They do that in a separate crate, which is
Exactly.
not on crazy.io.
Yeah. And our problem is that DNS is full of variable size data. Just almost every single thing in there is variable size. And so while I initially did try to use zero copy, it just was not feasible. I could not represent enough things using that. And so what ended up happening was this in-house zero copy thing has grown as a small little module now within the domain code. And it's more flexible than zero copy. It doesn't try to address exactly the same use cases. Like zero copy is formally verified, right? My code uses a lot of unsafe and it is not formally verified. And that's just the trade-off. But I tried to design something which is at least partially zero copy, but it will also be able to handle all the variable size data that DNS will throw at us. And so in a lot of cases, it can represent things just entirely as references into raw bytes, right? Which is the zero cost, that zero copy case. And in a few cases, it'd be like, well, I need to copy some things out. And that's sort of where that was what our trade-off ended up being. And so, I mean, we've heard from some people that they really like to see this module become a separate crate, and that's something that we'll try to explore at some point. But it's really interesting to compare and contrast zero copy with this internal module. The other sort of important departure from zero copy is that zero copy, all of the traits that zero copy gives you to implement, you can't really implement yourself. Or like if you implement them, then I think it's just if you try to first you can only implement them through the derive macros, and if you try to do things yourself, you'll discover that there's some private types and stuff. You can't actually do any of that
for good reason.
Yeah, for good reason, which is that zero copy will assure you that it will perform the deserialization and serialization correctly, right? And in the module that I ended up coming up with, each of those traits can be implemented manually where you need to, but there's also derive macros which will usually do the right thing. And so our goal was we just needed to make serialization and deserialization as efficient as reasonably possible while remaining really convenient to implement. So, for one of the really cursed elements of the DNS wire format is domain names. You can have domain name compression, which is this whole thing. I don't want to get into it. I've had enough nightmares there. But so we have specialized trait implementations just for domain names so that we can serialize and deserialize them correctly. Meanwhile, any of your high-level record types will just use the derive macros. And so we've ended up saving on a lot of boilerplate while still maintaining a lot of zero copy stuff. That was really interesting. We don't have proper benchmarks yet. That entire API is still sort of coming together and being fleshed out. We're making a lot of changes along the way, trying to make things more flexible or taking advantage of new Rust features when we're in the opportunity, right now domain's in this place where we're expecting to make a major breaking release soon. And so we're like, okay, well, we can redo our APIs now. We can now take advantage of async FNs in traits, things like that. That's all of that. So yeah, that whole architecture is evolving, but at the core, it's able to do a lot of zero copy stuff.
Very cool. And anyway, I think Joshua would be very proud of you because more than his promotion of zero copy, Crate, he wants to mostly promote the spirit of it and how you can do it. And that's also why he's in this working group on bringing some of it in the Rust compiler. So please do share the link with me to the module because I think he will probably be looking at it. I'm sure you will find it very interesting.
That'd be really cool. I'd love to. Well, if he's listening, then please get in touch. It'd be a fun conversation.
I will share it with him. He will see it. So do share. So yeah, sadly, I have a feeling we have to round off because as much as I could talk with you guys the entire day, we do have to somehow keep it into a limit. In the future, probably in season 2, I might do some roundtables around specific topics, and then I feel like I'm definitely be able to invite one or both of you at that point as well if you have me. But before we sign, okay. And then before we sign off, I do want to give you at least the opportunity to bring something up that you think we didn't discuss yet. It could be a topic, it could be something that you want to shout out, something that you want to promote around, maybe ask more funding around, anything you want really.
Go first.
Well, funding is always welcome. No?
Yeah.
No, I think I just want to shout out the organization here. Like NLnet Labs is been a fantastic employer, and they let us do a lot of cool stuff. Work on a lot of these things. They let us, as relatively new hires, take on these big cool projects, and I'm very grateful for them.
Yeah. I'll also give a shout out to Rust Week, which is May 18th to 23rd, I think. We'll be volunteering. Well, Terts is organizing. I'll be volunteering. Please come. It'll be so much fun. And I know I have a lot of side projects, but I don't feel like I think they're all too cursed to share publicly. There's some hash tables and things going on. But anyways, yeah.
We'll share your zero copy stuff, and then
We'll share my zero copy stuff and we'll call it a day. I'll just say that I do a lot of optimization stuff, and there's always more to talk about. But anyways, yeah, thank you so much.
Maybe you have like a blog around that we can also share, or
I do.
Is that not something you share?
Yeah. I do. Yeah,
So
sure.
I'll definitely put that in
blog.
share with me. Share anything of these things, like where people can find you. I will definitely also share that, and then they can become like a subscriber and follow you and see all the Curse projects.
I really appreciate
I think many
that.
people would like that. It's fantastic. Yeah.
Very cool. Well, thank you very much both for your time. I know you're extremely busy with all the wonderful work you've been doing, and I've been glad that we finally found a slot.
Yeah, thank you for having us.
This was really fun.
netstack.fm is brought to you by Plavayo, building secure, open, and resilient infrastructure with Rust, protocols, and purpose. This show is also made possible by Rama, the open source networking framework. Plavayo offers service contracts and welcome sponsorships to keep building and supporting its ecosystem. The theme music of this podcast was composed by DJ Mailbox. If you enjoyed this episode, don't forget to subscribe on your favorite podcast platform and leave a 5-star review. It really helps others discover the show. Thanks for tuning in. We'll see you next time for the next handshake.